Some of my students have trouble understanding these topologies. So this circuit is the exact same as this circuit. If you have to, pause the video to try to understand it. We have a MOSFET device for the common source stage and the resistance tied between the drain and a battery, we call it VDD. Again, you can see that this is the same as here. The resistance and the battery are actually in parallel to the MOSFET and whatever we could have here. All right, and obviously there is an input voltage connected to the gate. This is grounded, this is grounded, it just means that the voltage here is 0. We also add a voltage here, a battery here. Why? Because in reality, the signal we have here is small, all right? And it's so small that it's deliberately small, because if it were larger, we would have trouble with the operation of this device. So we want a small signal here, a quite larger battery here of higher voltage, just so we are in the saturation region of the device. For the saturation region, we want the gate source voltage to be larger than VTH, the intrinsic threshold voltage of the device, about 0.5, 0.7, and we want the VDS, the voltage from here to here, to be larger than VGS minus VTH. If you are new to the MOSFET devices, I suggest that you watch my video on the MOSFET devices, which goes into more basic stuff like this. Now, this VDD voltage is obviously a battery here, right? With a positive terminal connected to the RD and a negative terminal going all the way to the ground. We are going to use a small signal model of this topology, but before we do it, we must understand that the small signal model is valid only for the saturation region. Now that we ensured that we are in the saturation region, when we do the small signal model, we must ensure that all constant voltages, all constant sources become 0. Therefore, our batteries must become short circuits. So, if I assume no channel length modulation, my circuit becomes this. This voltage source became 0, therefore a short circuit, same as the VDD, all right, became a short circuit, that it should be here. The small signal model of the MOSFET device is this, all right, and this is what we call an AC ground. The AC ground is not the actual ground. It's very similar, it works the same way, but it's only in this case where the constant voltages have become 0. Now, this voltage difference here between the gate and the source happens, all right, happens to be the same as Vin. This is a current source tied between the drain and the source, which has a current, a value of GmV1. Gm is a property of the device, a transconductance of the device, and V1 is this voltage difference, the VGS difference. Also, this current here must also flow from here to here, because it can't really flow to the output. This voltage difference is V out, so the current must be V out over RD. Careful with the polarities here. That's why I drew the arrow from here to here, not the other way around, because we measure the voltage V out from here to here. Okay. All right, taking the KCL here, GMV in plus V out over RD must be equal to 0. Both of these come out of the this node. Therefore, V out over V in must be equal to minus Gm times Rd. Alright, this is always true for whatever topology we have here, as long as the source is grounded and between the drain and VDD is some type of resistance, or there is some type of resistance between here and all the way to the ground, or with another battery. In reality, if we do this, the small signal model for any type of similar configuration, for example, if we had a resistor, let me draw it like this. Alright, this is a resistor between here and VDD, or a resistor between here and the ground, something like this. These resistances would be in parallel to this resistor. So we would have actually V out over V in is equal to minus Gm times Rd in parallel to this resistance in parallel to this resistance. Now what if we had actually channel length modulation? Well, in that case, we would have an extra resistance tied between the drain and the source of the device, a resistance of Ro, which will not be infinite, alright? When we had the channel length modulation, symbolizing it as lambda is equal to 0, then Ro would be infinite. Now it is not. And also, we know, I've drawn it like this here, but in reality, there's no actual resistance between the drain and the source. This is only valid only in the small signal model. But I added this here just so, you can develop your intuition into how these topologies work. So I noticed that because there is no resistance tied between the source and the ground, the RO that I've connected between here and here and the resistance of D between here and here are actually in parallel. So, as we explained before, the previous relationship we had between the out over V in and GMRD now transforms into this. RD must be in parallel to RO. And we can generalize this as we explained earlier, and we can put anything here that is a resistance tied between the drain and AC ground. So if we had a resistance between here and here, between here and here, or here and here, which is the same, these would be added here as parallel resistances. On to studying now the input and output resistance of the device, we are asked to find what is the input resistance from here to here. Alright, this is the input resistance because here is the input signal. Well, for this, we have to draw the small signal model and be careful now. We must set all independent sources to 0. This includes our input voltage here. This is akin to the Thevenin equivalent of circuit theory that we know and love from the past. And then we must apply this, we call this the Thevenin voltage, and measure the Thevenin current and apply and find the Thevenin resistance. I just called Vx, high X, and Rin. In that case, we draw the small signal model as we know it, and we connect a new Vx voltage source here. This is not the same as this. This, remember, has been transformed to a 0 voltage source. Well, in that case, if I am to measure Ix, obviously, there is no connection between the gate and the source. Therefore, headroom must be equal to infinity. In reality, this is true only for small frequencies because there is an actual capacitance here between the drain and between the gate and the ground, all right? But we don't really pay attention to it in small frequencies at least, right? There is a value called C ox, which is the capacitance of the metals or the other materials here. All right, but we don't pay attention too much to it. All we need to understand here is that whether we had a resistance RO here, whether we had a channel length modulation, it wouldn't really matter. Rn would be infinite, not the same. All right, now if we don't want too many batteries, and we don't in our circuits, and we still want to bias it properly, then we're going to add a resistance divider between the drain and the ground of two resistances, and we connect the input signal like this. All right, this is similar to whether we have a battery here and a voltage signal here. Again, I am to measure a ring, and in that case, there will be, this resistance will be connected to the ground, all right, the AC ground. This resistance will be again connected to the AC ground, and I will connect a voltage of Vx here, and I measure the current Ix. Now there is a pathway for the Ix to flow to, which is the two resistances in parallel. Again, this is true for small frequencies. If the frequencies were kind of higher, there would be a capacitance between here and here, and it would disturb the circuit. And because there are some issues with the cases that the input signal is actually zero, it would short my configuration here. I add the capacitance here, an extra capacitance. And in that case, again, for small frequencies, the input voltage would be zero, in case you see this topology somewhere. All right. It's important to understand that we use topology because, right, we don't really cover this in this video, but it's important to understand that we do it because if we had a short circuit here and the input voltage became for some reason zero, all of the current would flow through here to here, and we would not have a proper bias here. So this capacitance protects us from this. Now on to calculating the output resistance. Well, for the output resistance, we must do pretty much whatever we did before. There is a short circuit between the gate and the ground, obviously. And between the outputs and the ground is going to be connected a voltage of Vx, a current Ix. We must measure it. We notice that the voltage between the gate and the source is actually zero because this node is exact same as this node. These are both shorted to the grounds. Therefore, there is no current flowing through the resistor, the transistor, because the current is a dependent voltage source of GMV1, and therefore current must flow through RD. Therefore, our out is the same as RD. Now, what if we had the same case here, but with channel length modulation? And just for a variety, I had the topology of the voltage divider between here and the ground, just so we understand that this does not really matter when calculating the output resistance because it doesn't really play any role. So we see that this and these are grounded, this and these are grounded. So not really any current flowing from here to here. Therefore, this voltage difference is 0. And therefore, no current flows from here to here. So, all of the current must flow from the resistor RO and the resistor RG. Therefore, RG and RO are in parallel because this node is the same, this node is grounded, this node is grounded. Alright, RG is in parallel to RO. Again, this would not be the same case if you had some degeneration here, some resistance here. Now let's solve these exercises just so we understand that we are on the same page. V out over V in, we are asked to find it, and we are also asked to find out if the MOSFET is actually in saturation. We are given the drain voltage. Alright, this is very helpful. Again, this drain voltage that flows from here to here actually flows all the way to here if you remember the small signal model. No actual current flows from here to here. Why? Because there is a capacitance again between here and here. We are given mu and Cox. Again, this Cox, the capacitance we talked about earlier. And we are given the VTH of the device. We are also, to make our life easier, the exercise says there is no channel length modulation. Let's assume we are in saturation, alright, for now. V out over V in, if we remember from before, is minus GM times the resistance tied between the drain and the AC ground. Only resistance is this RT, which is 1 kilo ohm. The GM, the transconductance, is given. One of the relationships that gives us is this. Square root of 2 mu and Cox W over L times ID. W over L is given to us here. So if we do the math, it's minus 3.33. Now, in order for our region of operation to be the saturation region, we must prove that this and this are true. How much is VGS? Well, there is a relationship from theory. VGS is VTH plus square root of 2ID over mu and Cox W over L. This is given, if you remember, from the relationship between the current and the VGS. So it's the current is actually this value squared times this. And I just write it like this, which if you do the math here, is going to give us 1.1 volts. How much is VDS? Well, it's the same as if we did a KVL, but if it's not clear here, we can look at this logically. The VDD is between here and the ground. There is some voltage drop in the resistance here, and the rest of the voltage goes to VDS. So it will be like this. VDS plus the voltage drop here, which is RGID, is going to be the same as VDD. Therefore, VDS is equal to VDD minus RGID, which, if you do the math, is going to be 0.8 volts. Indeed, we are in saturation. How much is VGS? 1.1. How much is VTH? 0.5. So the difference is what? 0.6. How much is VDS? 0.8. So we are higher than this by 0.2 volts. So we are quite, not really deep, but a bit deep in the saturation region. Alright, so with the input voltage of millivolts, or for input voltage of a height of up to 1 volts, we would still be in the saturation region, or would be still all right. It would still be good. Everything would be healthy. And that's it. That's basically the common source stage. Right? There are these concepts can't be quite daunting. I suggest that you watch this video again if you have some questions. And if you want, you can also write me in the comments below, and I'm very happy to answer. Right? Thanks for watching. Study well and take care.